Hey everybody! Last time we talked about radicals, we introduced them, and we talked about the idea of how do you just simplify radicals in general following these three rules. And we played a couple of good examples. Today what we're going to do is figure out how can we combine radicals. How can we add or subtract them? And it's a little bit complicated, but we're going to use the skills that we just developed in the last video. Alright, a couple of rules here, folks. In order to combine what we call alike or like radicals, they have to have the same index. Remember, that's the same type of root here, whether they're both square roots or both cube roots. And they have to have the same radicand, which means the number on the inside or expression on the inside has to be the same. If those two things are the same, then we combine them. Okay, so for example, over here, I could combine the square root of 3 plus the square root of 3. Because if you check, they have the same index and they have the same radicand on the inside. So when we do that, we have one square root of 3 and another square root of 3. We have two of them. We have two square roots of 3. But we can't take the square root of 3 and try to add the cube root of 3. Even though they both have the same radicands, they are not the same type of roots. They're not the same indices, so we can't do it. All right, so we forge through more of section P2 today. All right, example number 1. Let's see. We have radicals. We have subtractions, so we have to make sure that they have both the same index. Yes. And yes, good. They're both square roots. And do they have the same radicand on the inside? No and no. Okay, but we're going to assume that. We're going to hope that they can add or subtract. So we're going to need to simplify each radical one at a time so that they are the same. So let's start with 48. Let's just break down 48 for a second and just ignore the 2 on the outside. And we'll come back to it. All right, 48. Any good perfect squares that go into 48? Well, I do know that 48 is, how about 4 times 12? Okay, and if I keep going, that's 4 times 4 times 3. Great. Okay. That means because these are square roots, I can take the square root of each one and pull out a 2 and pull out another 2. So this really turns into 2 times 2 times the square root of 3, or 4 square root of 3. Okay. So that's what the square root of 48 is. But now remember, there was a 2 in the front. Let's bring him back. This was 2 times 4 square root of 3, which is 2 times 4, those are my sort of like terms I can combine. I can't multiply into the 3 because that's inside the radical. So this would be 8 radical 3. Great. Okay, so you can see that this friend is now this friend. And we want to try to subtract this term over here. Now, use a little bit of logical reasoning here, folks. If we're going to be able to add or subtract them, we know they have the same index, but obviously we need to change this 27 to match this, because I can't simplify that 3 anymore. So I kind of know that I want this radical to be a radical 3 left over on the inside. Well, maybe that'll help us out. Knowing that you want a 3 left over, let's just look at 27 as a square root. And if I want a 3 left over, this has to be 3 times something that we're going to be able to rip out. And in fact, 27 is 3 times 9, and that's your perfect square that you can rip out, folks. You'll rip that out, and the square of 9 is 3. So the square root of 27 turns into 3 times the radical of 3. But if you remember, we had the 3 here on the outside. So let's bring him back. That's 3 times your square of 27, which is 3 radical 3, which becomes, combine the two outside 3's, and we get 9 radical 3. Okay, this is looking really great, guys, because watch this. Now we can bring everything together. 2 root 48 becomes 8 radical 3 minus 3 radical 27 is now 9 radical 3. Let's do our check. Do we have the same index? Check. Do we have the same radicand, the same number inside? Yay, we do. So now we can literally add or subtract these. Okay, the radical itself, I kind of think of this as like a big rock. Okay, I've got basically 8 rocks. I'm going to subtract 9 rocks. I should have negative 1 rock. Remember, each rock was a root 3, and we can get rid of the negative 1 and just call it a negative root 3. 8 minus 9 is negative 1. So 8 root 3 minus 9 root 3 is negative root 3. That's your final answer for number 1, folks. So look what we had to do. Before you add or subtract, you have to make sure you have the same index. Check. You have to make sure you have the same radicand on the inside. Check, check. If you started with the 27 first and simplified that, great. And then you can move on to the 48 and use a little bit of logic reasoning again to simplify that. All right, shall we try number 2? Let me make a little space here. So again, our answer for 1 was negative root 3. I'll try to keep that there so you can still see it. All right, well, number 2 is very similar, except we have some variables in there, and the roots are different in terms of, now they're cube roots, but notice they're the same, which is good, but the radicands are different. So let's simplify. All right, well, with the first one, I need to take the x, but notice that this is x to the 1 power, but I have a cube root on the outside, so I don't think there's going to be any x's that I can take out of the radicals. The x is going to stay there. Okay, but that's 16 though. Let's see. 16 is the same thing as 2 times 8. Well, that's good news, because I can take the cube root of 8 and rip out a 2. So now this becomes, how about 2 times the cube root of, there's a 2 left over on the inside, and the x we didn't touch because we couldn't bring him out. All right, this friend is good to go. Does that sound okay? Now, by logic reasoning, that means that if I want to be able to add or subtract these, then my inside radicand over here on the right needs to reduce somehow to a 2x. But again, use a little bit of logic. Let's use that knowledge to simplify this 54x to the 4th. Okay, so I need to have a 2x left in here. So watch what we're going to do. If I need a 2 left over, that means whatever's left after dividing 54 by 2 must be cube rootable. And in fact, if you see, 54 is 2 times 27, which is a cube rootable number. And I need an x left over, right? That makes sense, because I'm going to break x to the 4th into x times x cubed. Just like we did before, let's write it as exponents that match the index. All right, let's see what we can rip out now, folks. The 27 we can cube root, take out a 3. The x cubed we can cube root and take out an x. So this whole friend turns into the cube root, oops, let me put my expression in front, 3x times the cube root of, now what's left over on the inside? The 2 and the x. Now notice how the 2 radicands now match. Great. Okay. Ready to put it all together, folks? We have 2 cube root of 2x, and the original operation was a plus. We're going to add 3x cube root of 2x. All right. Same index, check. Same radicand, check. I've got 2 rocks over here. I've got 3x rocks over there. So I basically have, well, I can't really add 2 and 3x, but I'll just write it as an expression. I have 2 plus 3x rocks. And there you go. There is your final answer for number 2. So again, first step, just make sure you have the same index and the same radicands. And if you don't, just simplify until you do, and then you can add or subtract them, just like rocks. Good job on that. All right, but okay, adding, subtracting, fine, but what if we're dividing? Ew, well, that's kind of strange, and it kind of begs the question, well, what's wrong with that, Mr. Brown? Why is that bad? It's not that it's necessarily bad, but we realized long ago in older algebra and older mathematics that when you had the radical on top and just a number on the bottom, it was easier to mentally compute. And so we typically try to make the top have the radical and not the bottom. So in order to do that, if you remember from your algebra days, we have to use a special step called rationalizing. So we're going to rationalize the denominator in order to get rid of the radical on the bottom and make it easier to present. Okay, how are we going to fix? Well, basically, we want to get the root 2 to not be a root. We can't square it, though. That's really tempting, because doesn't squaring get rid of the square root? And it does. But when you square an answer, let's say your x answer is 3, you're like, okay, I want to fix it by squaring it. Well, when you square it, you actually get a completely different answer. So squaring it will change your answer completely. We want to be able to do something to our 1 over root 2 over here that doesn't completely change the actual value of it. It just presents it in a better way. So instead of squaring it, why don't we multiply the denominator by the same radical? Now, if I do that in the bottom, so I don't completely change everything, I have to do that in the same on top. Because if you think about it, root 2 over root 2 is just like basically the big number 1. So I'm multiplying 1 over 2 by some version of oneness, so it doesn't really change. All right. On top, you get 1 times root 2, coolio. On the bottom, you have root 2 times root 2, which is root 4, which works out nicely, right? Because the square root of 4 is 2. In general, you'll notice that when you multiply these two radicals, usually the radical will go away and you're left with whatever the radicand was, in most cases. Let's look at our answer. Is the denominator radical free? Yes. Are the radicals simplified? Yeah, we have a root 2. There's nothing more to do, so we're done. That's how we're going to fix. That's how we're going to rationalize. Shall we try number 1? Here we go. All right, what's the problem number 1? You see that radical down there in the bottom? Darn it. All right, again, we can't square it, but we're just going to rationalize it. So we're going to multiply by, well, the only problem with the denominator is just the radical, not the 2. The 2 is actually okay. So we don't have to multiply by, don't write this down yet, we don't have to multiply by this. Oops. You can. That's still the number 1. You're just going to have to simplify a little bit more when you're done multiplying. But the only problem here is the radical. So you don't have to include the 2 if you don't want to. So what if we just did the root 3 by itself? That should be enough. Okay, ready? Here we go. On top, we get 5 and root 3 don't really combine well. So it's just 5 times root 3. And the bottom, well, let's just deal with the roots for a second. How about root 3 times root 3? That should be root 9, which is 3. So you see how the radical goes away? Sweet. But remember, we also had the 2 down there multiplying. So multiply the 3 and the 2. Don't forget him. And we get a 6. Now let's just check and see. Again, is the radical gone from the denominator? Yes. Is the radical up on top simplified? Yep. And there we go. So 5 over 2 root 3 is the same thing as 5 root 3 over 6. No radical on the bottom. Great. I love number 2 because he's so strange. Because again, he's got a radical on the bottom, but he's a cube root. Is that going to change anything? Let's find out. Well, my first hunch is, what if we just multiply by, again, like Mr. Brown said, I'm going to multiply by the radical that you see on the denominator. Yay, Mr. Brown would be so proud. And I am so proud of you. But do you notice what's going to happen? Don't write this down yet. Watch what happens. If I multiply on top, I get 2 times the cube root of 5. No problem there. But on the bottom, do you see what happens? I actually get the cube root of 25, or 5 squared. The reason why that's weird is that doesn't cancel and give you 5. Not yet. Because the number inside, the exponent, doesn't match the index. There's really not enough 5s to get canceled and bring out a single 5 out of the radical. So it's almost like you didn't use enough 5s to clean out the radical. So here's the deal. Look at your index. I need 3 of those, right? That's our goal. I need to multiply by some number of them so that eventually on the bottom, I have 3 5s. Because once those numbers match, then the radical dies, and I'll just get a 5, and the radical will be gone. So I ask you this question here, friends. From step 1, if I know I have 1 5 inside the radical, how many more 5s do I need so that I can destroy it with my 3? I need 2. So we're actually going to multiply not by a cube root of 5, but we're going to multiply by the cube root of 5 to the 2 power. Because then that will add up to 3 5s, which will cancel the cube root. Isn't that strange? All right, so let me show you what I've got so far. I've got 2 times the cube root of 2 5s, 5 squared. On the bottom, I have the cube root of, well, I've got 1 5 here. I've got 2 5s, same base. I can add exponents, and I have 5 cubed. Yay! That's great. Look how the exponent matches the index. So they will cancel, and I can take a 5 out. So here's what you're left with. On top, you get 2 times the cube root of, you can leave it as 5 squared, or you can put it as 25. That's fine. Either way, you can see there's nothing we can do with that. We can't take any cube root or simplify that. All divided by 5. Let's check. Denominator, radical? No. Cube root, simplified? Yes. I wish we could do more with it, but no, that's it. So again, this is a weird one for number 2. I'll put a little star next to it. We don't see it too often, but don't just autopilot, blindly go in and multiply it by just the radical by itself. Sometimes you have to check the index to see how many more you need to do. Oh, gosh, we have to make it more complicated, Mr. Brown? Oh, so what if you have more than one term? Here I have a 3 and a root 7. Well, that's kind of weird. Like, how do I rationalize that? Well, let's try. The way we did before, we have a root 7, so let's multiply by root 7 over root 7. Let's see what happens. Okay. On top, we get 2 times radical 7. Cool. Now, on the bottom, because there are 2 terms here, we have to use our distributive property and multiply into both pieces. Okay, that's not terrible. 3 times the root 7 is just literally 3 times root 7, plus root 7 times root 7 gives you root 49, or 7. Oh, yay, that radical goes away. Oh, no, that didn't. So by multiplying by the same method as before, just the root 7 over root 7, we kind of got rid of one, but then we created a new problem. And you can see that if I actually said, all right, well, let me just clear that by doing it again, Mr. Brown. Yeah, that's a good idea. But again, once you distribute in, that will clean up, that will not. So we need a better way. And the better way to do it is by multiplying. When you see 2 terms in the denominator, one of them is a radical. We need to multiply by what's called the conjugate. Many of you might have heard this before. A conjugate is if you have 2 terms, the conjugate is basically the first term and the last term, but you change the sign in between. 3 plus root 7, the conjugate would be 3 minus root 7. What would the conjugate of 1 plus 2 root 3 be? Did you get 1 minus 2 root 3? Good job. Notice how we didn't change the sign of the front term. The front term is still a 3. Front term is still a 3. We're still a positive 1. He's still a positive 1. It's just that middle term that we change. How about negative 4 minus root 5? Just like I was saying, let's keep the first term the same, the last term, and we change the sign. Okay? These are all conjugates. Why? Why are we doing this, Mr. B? Well, let me show you. Why does it... Oh my gosh, I can't scroll down. Why does this work? Let's find out. We started with 3 plus root 7 in the denominator. Our conjugate is 3 minus root 7. Let's just multiply these two together. What happens when we multiply a number by its own conjugate? Ready? We have to FOIL here. So let's do our first, which is 3 times 3. We need to do our outers, which is a minus 3 times root 7. We have to do our inners, which is a positive 3 times root 7. And then finally we do our lasts, which is positive times a negative is a negative, and root 7 times root 7, root 49, or 7. All right, can you see what happens to the outer and the inner term that we did? They're opposites. They always will be when you're doing conjugates, so they're gone. Poof, get out. And you're left with just a 9 minus 7. Why is that great? Well, look at your answer. Do you see a radical there? No. So we need to rationalize up here on the top here, folks, but you have more than one term, we're going to need to use the conjugate. Shall we try it? Let's see. Okay, let's go back to the original problem here, number 1. And now you see 2 terms here? Let's multiply by the conjugate. So the conjugate of 3 plus root 7 should be 3 minus root 7. But remember, same rules apply. If you multiply that in the bottom, you have to even it out by multiplying on the top, same thing. Okay, now I'll show again the steps. On the bottom, we're going to have to FOIL. On the top, we're going to have to distribute. Great, here we go. 2 times 3 on top is 6. Minus 2 times root 7 is just 2 root 7. On the bottom, again, we had FOILing. So 3 times 3 minus 3 root 7 plus 3 root 7 minus square root of 49 is 7. The inner numbers always cancel. And you get, on top, nothing to do here because they're not alike radicals. One's a radical and one is not, so you have to leave it. On the bottom, we have 9 minus 7, which is 2. Radical on the bottom gone? Check. Radical on top simplified? Check too. But there's one more thing I do notice just out of the corner of my eye. Do you notice how every term is divisible by 2? Huh. So maybe I can simplify a little bit more. Let me just sort of factor out a 2 out of every piece. if I take out a 2, and we'll talk more about factoring in P3 to recall how we did that back in algebra days. But if you remember, I'm going to take the greatest common factor of a 2 out. And when I do that, I should have a leftover of 3 minus just 1 root 7. And the 2 on the bottom is still there. That's great because look what happens to the 2 on the outside. Goof, and the 2 on the bottom. Poof. And your final answer is 3 minus root 7. Look how pretty that turned out. We started with this monster up here. We did some really cool conjugate rationalizing. And this is my final answer. Nice, folks. Why don't you try number 2 on your own? And then we'll catch up with each other and see how you do. All right, number 2 here, friends. All right, do you notice we got 2 terms in the denominator, so we can't multiply by just one of the radicals. We have to do both, and in fact, we have to do the conjugate. Did you pick root 2 minus root 3? Bravo, nice job. All right, let's multiply. Again, on top, we're going to distribute. And on the bottom, we're going to FOIL. Let's do the top. How about 6 multiplies the root 2? The 6 multiplies the root 3. See, we can't really simplify much of that. They have the same index, but they don't have the same radicand, so we can't combine those. Oh, well. All right, let's FOIL the bottom. The first, root 2 times root 2 is 2. On the outsides, we have a minus root 2 times root 3 is actually a root 2 times 3. On the inners, we have a positive root 3 times root 2. That's, again, root 3 times 2. And the last, how about minus root 3 squared minus root 9, or minus just plain old 3. Okay, look at those middle terms. Poof, poof, they're gone. On top, folks, you have 6 root 2 minus 6 root 3. On the bottom, all you're left with is 2 minus 3, or negative 1. Really good, really good. When you divide by 1, usually you can just leave the numerator as is, but we're dividing by negative 1, so I think it would be great if we could divide each piece by that. Let's separate and divide each piece by the negative 1. So I really get 6 root 2 divided by negative 1 minus 6 root 3 divided by negative 1. And that is, well, that just changes the sign of the first one. Remember, with the properties of negatives, that just turns into a regular negative 6 root 2. It changes the second one to a negative 6 root 3, but we're also subtracting here, so that basically turns into a big plus. Okay, this is one way of doing this, but if that was really strange, folks, another way to get rid of the negative on the bottom is just multiply the top and bottom by negative 1 over negative 1. That will destroy the negative on the bottom. It'll distribute into the top, and you'll get the same answer here, folks. Good job on that. So again, the purpose is if you see 2 terms in the denominator, and one of them, at least one of them, has a radical, we need to rationalize with the conjugate. Next time I see you, folks, we're going to talk about these strange guys called rational exponents. We know what rational means. We know what exponents are, but what happens when they're rational? Something like 3 to the 2/3 power. What does that mean? Tune in next time. Great job today, friends.